Good morning and welcome to the 41st Annual Winter Star Party.
Hi, I'm John Panek. I'm here at the 41st Annual Winter Star Party at Scout Key. I'm going to be giving a talk about the Nancy Grace Roman Space Telescope. I hope you enjoy it. Thank you for coming. I'll be talking about the Nancy Grace Roman Space Telescope. It's NASA's next large observatory. I had to make a decision kind of, what level of information to present. You guys are, serious amateur astronomers. So I left out quite a bit of the things that you can Google in 5 seconds on your phone. So if please stop me if I'm speaking to the deeper level of details that, if it's not making sense and I skipped over something, please stop me and happy to answer. But I thought, I can give you the next deeper layer, right? Because I was in there on the project for 6 years, and I figure, everybody's got a phone, and on the laptop you can check the Wikipedia page and get, 90% of the information. I wanted to give you that 10% deeper level. I talk about the finances, how much the mission costs, things like that. So anyway, let's get moving. So I'll just flash up a page about myself so you know my background, then where the project sits in NASA's portfolio of large telescopes, back from Hubble and James Webb and a future telescope I'll mention. The history specifically of this telescope, it's morphed through the years. I think back in the 2010s, it was a slightly different concept that's changed. I'll show you. Then the science program, where do the requirements come from for what technical performance and functional requirements that the observatory has to meet? And that comes from the scientists. They decide what we'll do. And I'll show you how that works. And then finally, for the last half, I'll talk about the hardware. Just an amazing telescope. If you're susceptible to aperture fever, you might want to look away at one of the slides. It's pretty cool. But I'll go through the major components that stack up into the full observatory. Okay. So as I mentioned, I've worked at JPL and NASA for 27 years. I started in low temperature physics, cryogenics, technology development enabled from those areas. I've worked on a few winning proposals. I'm proud of working on Da Vinci, TESS, and Lucy. And then around that 2010 era, we were talking about, I worked in the Integrated Design Center, so over 60 different concept studies for instruments, missions, and architectures. And then the 3 flight projects I've worked on are the Roman Space Telescope for 6 years, the Astro E2, which was renamed Suzaku, the Japanese observatory with a Goddard instrument, X-ray spectrometer on board. And then on the Roman systems team, there's 25, 30 of us or so, just as mission systems engineers, trying to coordinate the activity for hundreds of engineers in the different subsystems. And I did basically paperwork, requirements development, verification and validation plans to make sure we're meeting those requirements, and then the interface controls among all those all these major elements of the observatory. They have to talk to each other. They're bolted to each other, and so how do you make sure it all fits together and works well? That's the sort of thing I did for 6 years. So moving on to the where it fits in the NASA portfolio, these are also called flagship missions. You may have heard, if it's kind of over $1 billion, then it's a flagship mission. It gets all the special attention, and they're usually directed. Headquarters directs NASA Center or JPL to work in some way on these large missions. In the 4 divisions within the Science Directorate, we fit into the Astrophysics division. So the same division that gave us Hubble, Compton, Chandra, James Webb Space Telescope, Roman Space Telescope, and the next big one will be the Habitable Worlds Observatory. So that's going to be really nice. And I mentioned, we'll talk a little bit about the money. I looked through, this is all public information, but if you sort of, they're not quite all at the same year dollar amount, accounting for inflation. There's a 1 or 2 year difference, but basically Hubble cost around $16 billion total from start to all the operations. James Webb Telescope launched recently, about $10 billion, including 5 years of operation. We're just a bargain at only $3.3 billion. So that's, but that doesn't include the contributed instrument from the Jet Propulsion Laboratory, that's the coronagraph, and a little bit of reserve money. And then the next big one, the Habitable Worlds Observatory, I have no idea what that will cost. I don't even want to speculate, but that's a big one. That's 3 times larger diameter mirror, and but 20-ish years from now, 15, 20 years from now, that's when it would be launched. Okay, so let's see, next, the glory shots of the big 4. I didn't include Chandra here, but just an oversight, but Hubble and James Webb, of course. This is latest concept of what Roman will look like, a sun shield and solar panels on top, and the optical components in the middle. I'll show you much better pictures than this. This is just a nice public shot. And then this, the Habitable Worlds Observatory, one of 3 concepts that are being developed. Three different engineering teams are working on concept studies now. That's just one of them. Okay. So I mentioned, I almost forgot. This is the right place to mention it. So in the mid-2000s, this began as the joint dark energy mission. So NASA and the Department of Energy were cooperating to build something to address these cosmological questions about dark energy, dark matter. And then in 2010, it was renamed the Wide Field Infrared Survey Telescope. And so, focused on a new effort to use one of these donated mirrors from the National Reconnaissance Office. They had a couple of spare mirrors available, optical telescope assemblies available that they weren't going to use. And Congress said, to save money, NASA will use these donated equipment. So other government agencies build and test things differently than we do. And so we had a review and checked all the paperwork and ran tests to see, can we use this piece of hardware efficiently? And we decided we could. Right around that same time in 2017, there was an external independent review that really shifted focus a little bit. I'll talk about some of the changes, but basically to cut costs in certain areas, to manage the program more efficiently, and some pretty interesting changes from that external review. And then at about the same time, this 20 different ways to arrange the optics, and what's the best architecture to do that. And it's an off-axis 3-mirror anastigmat was selected, and I'll show you more of that later. So after that external review, we really got going. We passed a systems requirements review in 2018, the preliminary design review in 2019. At that point, it was renamed the Nancy Grace Roman Space Telescope, after Nancy Grace Roman, NASA's first chief astronomer, known as the mother of the Hubble Space Telescope, because she really pushed for getting that large space telescope in orbit. A few years ago, passed a critical design review, and that's when things really took off. You'll see the hardware and where it is now. But the launch, the hardware is all coming together, and for the next couple of years, we really have to test it, make sure it'll work when it's launched. There's no sending an astronaut out to fix it like you could with the Hubble Space Telescope. So it really has to, just as the James Webb had, I think, over 100 single point failures, that any one of which could have, in all that deployment of the unfolding, any one of those stopping would have seriously endangered the mission. So we really have to, I'll just mention this external review in 2017. We were managing the observatory to a risk profile. There's, Class A missions are the human space exploration, the flagship missions are Class A, but we were managing it to a Class B, which allows us to take a little bit more risk. And there are other missions like CubeSats are Class D, most small spacecraft are Class C, and that just gives us specific guidance on how to take risk, because you can't eliminate risk. There's 100% guarantee of success will cost infinite money and take infinite time, so we can't do that. We have to take some risk. But the review said you can't manage a $3 billion mission to Class B. It has to be Class A. So that increases the cost. And then we did other things to decrease the cost, just to give you some idea. So this will launch in no later than May 2027. And the orbit is the Earth-Sun L2 Lagrange point, similar to where James Webb and several other observatories are out there now. And then designed for a 5-year mission reliably, but it has consumables, propellant on board for 10 years. And I'll talk a little bit more about things that let us operate longer. Okay, so that's the context. Now moving on to the science, how we decide what science to do. There's every 10 years a decadal survey from the National Academy of Sciences. They publish, this is the cover page of a report from 2010, and they give priority to the science questions they want NASA and other agencies to answer. What's most important now in the astrophysics community? In 2010, it was this New Worlds, New Horizons report. And so it had 3 explicit science objectives: the expansion history of the universe and growth of cosmic structure, the search for new populations of extrasolar planets, and then a broad range of kind of general astrophysics questions. But those first 2 are the main ones. You'll see in the time budget of how the telescope spends its time, I'll show you, that kind of shows how the telescope's going to achieve these 3 objectives. And then this is primarily done by one, this is mostly done by a wide field imaging instrument. So just a camera with a wide field of view in visible and infrared light. The technology demonstration is done by the Jet Propulsion Lab's coronagraph instrument. So this is going to demonstrate active wave front control in space of an interferometric coronagraph. So detecting, directly imaging planets, not just detecting them, but imaging them, 50 light years away or so. And but this is from that independent review. This is not a formal science instrument. It's a technology demonstration instrument. So it's going to demonstrate these technologies, and then we'll refine based on what we learn into that next telescope, the Habitable Worlds Observatory. That's the one that's going to, of course, we'll get science out of this one, but we really have to get ready to do the science first, because you'll see. I'll explain better. But that's, the hardware, the software, the data processing, all that has to be demonstrated. Yeah, please. So there are, I can't give you a great answer because I'm not a coronagraphic scientist, but from what I understand, they're they're splitting the light and then recombining the light from the star to cancel itself out. And the fact that the planet is on a different line of sight, the light from the planet does not get canceled out as efficiently. So there are all kinds of optical aberrations in the telescope. There's, I think, 7 or 8 optical elements before it even gets to the coronagraph. And so everything has some aberration, and that needs to be canceled out. and it changes very slightly. Those aberrations change as the telescope shifts and a reaction wheel will spin up or the antenna will move. There's jitter and drift in the telescope that you have to sense actively over, say, a 10-hour exposure. You have to be correcting the phasing of these two light beams before you recombine them. Okay, so this has not been done in space before. It's done on the ground, with artificial stars. The coronagraphs can combine interferometrically, recombine the light, but this is the first one to do it in space. Okay, did I answer your question? Oh, okay, so as best I can. I'm just I'm a mechanical engineer, so. Okay. Yeah. I will show you how it is modified. I have a slide specifically for that. I'm not sure how they sense the wavefront, but I can show you how they modify it for sure. Okay, so those were the top level science objectives, and then to fulfill those objectives, we have to write requirements, and then we have to build hardware that meets those requirements. So these are the top level science requirements. Do these surveys, run these programs for galaxy redshift, weak lensing, supernovas, micro lensing, and then general surveys. The technology demonstration requirements for the coronagraph, these I'm not as sure. I don't have access, I have access to all the Roman and wide field data that we're doing at Goddard, but this one is at JPL. So if there might be a higher level top requirement than these, but this is what I could find. The types of stars it's going to observe, magnitude brighter or equal to 5. And then the exoplanet 10 million times fainter than the host star. The technique I described to you where the coronagraph cancels the star, it dims it about 10 to the 9th, a billion times dimmer. And then the planet is dimmed a little bit also, maybe 10 to 100 times. But so the relative brightness of the planet is 10 million times the original view. And then there's a couple different modes that it has basically a narrow field of view and a wider field of view. And then just generally the working angle near the target star. We can't image right next to the star. We can't image very far away from the star. There's a sweet spot there. Okay, then again, those top level requirements say what we need to do. And then this is starting to get into how we're going to do it. And then on the right, there's the percentage of time that I've taken from the concept of operations document and added it all up. And this is how much time high latitude, wide area surveys, both imaging and spectroscopy, the high latitude, wide area survey, deep field observations, which longer exposure times for the same field. These other surveys, imaging, a general survey here is the people propose, I want to look at this or that, and it's peer reviewed and they're awarded time on the telescope. That's the largest fraction, 31% of the total time. The coronagraph gets only 5% of the time as a technology demonstration. Over 5 years, 5% of the time. And then it can certainly change as people make decisions after 5 years, I think. Then a lot of calibration. We really want to get the make sure that the data we're delivering is calibrated for, and there's an internal calibration source. That wide field imager flies with its own set of special LEDs to to calibrate those sensors. And then a little bit of engineering overhead. And I think that adds up to 99% of the time for rounding. And then again, how the telescope functions still. There's a field of regard where, the field of view, what field of view is obviously, but then where can you point that field of view? We can't image targets below the horizon here, for example. We can't look at the sun unless you have a solar filter, things like that. So our telescope can't point to within 54 degrees of the sun, but it also cannot point more than 126 degrees away from the sun because of stray light issues. You obviously don't want sunlight coming down the barrel of the telescope, but also in the back of The telescope, similar reasons. So there's this large angular space. If you guys are the sun and I'm the telescope, there's this large angular space where it can image. It can also roll around that line. The solar panels are slightly larger than we need, so they don't need to be straight at the sun. They could roll on the bore side of the telescope, plus or minus 15 degrees. And then this GB is the galactic bulge. We can image that twice a year. So it's seasonal. As the Earth goes around the sun, there's this large field of regard, but that field of regard rotates during the year. So you can image the entire sky. Then I also wanted to give you an idea a little bit for these large observatories. When you change targets, how long does it take to move this thing around? The top row, the gap filling, you'll see these detectors are tiled together. So there's a little gap that's not imaged between the detectors. We want to catch that, so we'll shift just slightly, just a small shift in pointing lets us complete, so it's uninterrupted space. Then the field of view of that imager is like a curved rectangle, you'll see later. But the curved rectangle gets imaged, and then it's shifted on the short direction to make up this area survey, and then shifts over in the long direction to get to the next column. And those times, 40 seconds, 50 seconds. A whole 90-degree slew will take 180 seconds. So what is that, half an hour to slew 90 degrees. And this is a fairly agile telescope too. It's got 6 reaction wheels that can move it around. So that's how all these science programs will be implemented. And then finally, I get to the hardware. This is what's going to do those science programs. So this image was taken in a clean room at Goddard about 2 months ago. All the hardware has come together. So I'll use my high technology stick here. Starting from the top, you recognize the secondary mirror on trusses. The primary mirror is in here. And then there's a bunch of relay optics in the middle to get light from that telescope out to the instrument kind of down in here. This is the wide field imager, this large assembly on the left. And then the coronagraph, there's another set of relay optics that take it over to the coronagraph over on this side. Both the wide field and the coronagraph are held inside this truss structure. That's the instrument carrier. And that is bolted to the telescope. So the 2 instruments, the telescope and the instrument carrier, are all solidly connected and very stable. Now the spacecraft down here below, it's got an antenna that's moving. It's got reaction wheels that are spinning up and down in rotational speed. So it's the source of a lot of disturbances. And so there's a better picture later, but I want to point out there are these struts here. There are 6 struts, 4 of which you can see here. These little cans are vibration isolator systems. They're these huge, dash pot kind of spring dampeners that isolate all of that, all of the optics from the spacecraft to get a nice, stable, low jitter environment. And then I mentioned the spacecraft down here. This is a hexagonal structure, aluminum honeycomb panels. Everything's inside there, the propellant tanks and all the equipment you need to make a spacecraft run. And this is the current state of assembly. So it's going to get tested a whole bunch in this configuration, and then a large outer barrel assembly will be lowered on. I'll show you. I think it's the next slide.
Is that about 30 feet high?
Oh yeah, thank you. Thank you. Right down here, there are 2 people in clean suits here, in the bunny suits in the clean room. So 30 feet, not that many. That's that's one of those basic questions. I thought, you stumped me. But yeah. It fits. Yeah, it's about.
By the time you put
Yeah,
that thing on.
five people. This part doesn't launch. This is just some ground support equipment so we can move it around. You can mount this to a large fixture to hold this vertically or horizontally, depending on what.
The guys are going like this.
Yeah, exactly. Stack them up. Yeah, and it's taller too. Like the optical barrel assembly is obviously above the secondary mirror, and then there's some additional. There's like an aperture door as well. On top of that, we launch with the door closed. Like yeah.
Who's going to
Please.
put that up in the orbit?
It's a Falcon Heavy. Yeah, the Falcon Heavy can.
Sounds like Elon.
Elon's rocket. I think their capability of that launch vehicle is around 10,000 kilograms for this orbit, and then all fueled up and with all the hardware, this is about, I want to say in the high 8,000s, maybe low 9,000 kilograms. It's a big one. Okay.
How heavy was the one that's up there now?
The James Webb.
Yeah.
I can't give you an exact number. That was launched by an Ariane 5, so comparable in size, I would say. But I can't. I would guess more than 5,000, less than 15,000. But yeah, it's a lot of kilograms. What is that? 5 tons, something like that.
Do you know what they charge to put that up there? Any idea?
I think I do. Yeah, the Falcon Heavy, I want to say is like $250, $300 million price range. Mm-hmm. So,
Like an Uber ride.
yeah, yeah. Those launch costs have really come down.
Launch costs
Yeah,
come down?
that would. I think that Ariane 5 was something like double that. I'm not sure exactly, but it was contributed too. So we didn't pay for it. But if you were to buy an Ariane 5 for your own purposes, I think that's the kind of the amount.
250 million?
I think so. I think that's roughly what a Falcon Heavy costs, and it depends too. It depends on if I think they charge more for a government launch because we require more paperwork, and we cannot buy insurance for our payloads, right? So we need more verification and more reliability. A commercial company pays less, but they buy insurance, right? And so those launch vehicles, I believe, are verified or have less paperwork. I mean, they're obviously still safe, but we're the government. We need a lot more. Is there? Yes.
What percentage of that is for fuel?
Say again.
What percentage of that cost is for fuel?
Cost?
Yeah.
I'm not sure. But the fuel is hydrazine fuel. I think there's 2 flavors of hydrazine. There's regular and high purity. I forget which one we use, but I don't think that's that very much, to be honest. I'd have to look it up. Sorry. Please.
How are the sensors cooled?
How are they cooled?
Yeah.
That's a good question. Let me back up. So they're cooled. I'll say it this way. So the optical telescope points out through the barrel assembly into deep space. So it's cooled radiatively, and the primary mirror runs at about 260 Kelvin. I can't do the conversion in my head to Fahrenheit, but say again.
I used to work Go satellites as an engineer.
Okay.
We had coolers and all. I was
Yeah.
kind of curious. I didn't see it on here.
Exactly. Yeah. So observatories like James Webb has cryocoolers in the instruments, but I think largely it's cooled radiatively. And so if you put an efficient enough sunshade and thermally decouple it from any sources of heat, it will cool off if you're just staring at deep space, right? So our primary mirror runs at 260. The wide field instrument here these are all radiator panels, so it's radiating into deep space, and I forgot.
Like a cooler.
Yeah. I don't think it has active coolers. It's all passive. For ground testing, though, it does require a ground system to cool it actively, and that's a source of vibration, so it has to be compensated for in the ground test. The outer shroud is liquid. I'm not sure about the details, but we can do either nitrogen or helium. I'm sure Webb was tested in a helium environment. I'm not sure that we're using helium or nitrogen. I just don't know at this point. But it's in a plan somewhere. I could tell you if I looked for it for half an hour, but I don't know off the top of my head.
Thank you.
So please. Anything else at this point, please? No? Okay. Okay, so what the actual hardware you saw was this level of assembly here, and that breaks down into the spacecraft bus. You see the fuel tanks in the middle, these 6 bays. They have hinges on the side, and these panels just fold out, and you have all your hardware on the inside. You install it, and then you close up the panel. So there's these 6 equipment bays. And then underneath there's a deck that holds the communications antenna that's folded up down here. It'll deploy out and track the Earth from down here. Propulsion module, I'll show you later how that integrates up into the bottom spacecraft deck here. And then more exploded views of the instrument carrier and the 2 instruments here underneath the telescope there. Okay, so that's the overall architecture. Okay, so I'll start focusing on those components. This is the optical telescope assembly, the trusses, the primary mirror, baffles, secondary mirror. Here's a bunch of relay optics, this tertiary optical mirror assembly for the coronagraph, and the aft optics module for the wide field instrument. And then here you see the ray trace from deep space, primary, secondary, to the relay optics. And there's 2 zones that are both illuminated. One set of relay goes over to the aft optics module into the wide field instrument. The other set is this tertiary collimation assembly that goes down into the CGI instrument, coronagraph instrument.
How many mirrors and all that?
So it's a total of 11 primary, secondary, pick-off mirror, a couple in here. It's either 10 or 11, and one of them in here, I think it's this element right here in the AOM, has an entrance aperture plate. That's the final stop to block any stray light. If you have stray light bouncing in here at some crazy angle for some reason, maybe the moon is close to the edge of the field of view or something. If this actually just happened, the Gaia spacecraft is the European Space Agency's astrometry spacecraft that just finished. It's completed its mission. It's going to be moved out of this orbit in the next month or so. They had their optical barrel assembly that shades all this has a very black, non-reflective composite. But when you cut that composite into shape, the edges, the fibers poke out of the edges, and the fibers are shiny. So they had some stray light problems. So that's a really strict requirement. They do the stray light analysis is just people do a lot of work. Yeah. We have very sensitive instruments. We don't want to spoil them with unnecessary stray light. But yeah, 10 or 11 mirrors and one entrance aperture plate, even before it gets to the instruments. Okay, so this is the one. Don't look at it if you have aperture fever. This is the Hubble size, 2.4 millimeter f7.9, and it's the same dimensions as Hubble, but it's only a quarter the mass. So it's lightweighted compared to Hubble. So this was the donated spare. We stripped the old coating, refigured it with the ion beam machining and whatever else they did, and then resilvered it. So we use silver. We have shorter infrared wavelengths compared to Hubble. Hubble uses the gold coating, or not Hubble, excuse me, James Webb. Thank you. Webb has the gold coating on the beryllium mirrors. We have silver coating on ULE glass mirror. Then a tenth of an arc second per pixel on the detector, 20 nanometer RMS surface figure error. And then this is all obviously tested on the ground in the Earth's gravity. We have to compensate for that and subtract that out of the performance we expect on orbit. So this is tested vertically, and then it's flipped up on its edge and tested horizontally in several different orientations. So you really want to, they spend a lot of time figuring out how to float this thing to support it for testing, and then a lot of time goes into, getting. I'll talk a little bit more about the verification and validation too, so we don't repeat the Hubble mistake that got launched, right? So this is what I'm talking about. So independent cross checks this says at every level of assembly. I think in some cases it's a cross check, maybe a test and analysis. I'm not sure, but there's all these components are, just when the component is made, it's tested, and then when it's assembled, it's retested, and they call it the two-factor testing. They want to really verify that it's being built the correct way, with independent cross checks. And so all these parameters are measured. The instrument beam quality. In some cases, there's a 10-hour exposure time. So as the telescope changes over those 10 hours in levels, at very small levels, but at levels that we want to know won't affect the optical beam quality. So here you see this is one of the tests. This is that structure, some cooling shrouds, and then a 2.7 meter diameter flat. This is all suspended with cables from the top of a test chamber. And then you can just imagine the amount of vibration isolation you have to get a good stable. There's no person in there for scale, but it's an 8-foot diameter primary. So that's our largest test chamber at Goddard, thermal vacuum chamber. Then these are just optical and thermal tests. Mechanically, this thing gets launched. It has all that random vibration, acoustic loading, shock of the being released from the launch vehicle. All these things are tested. The life testing of the actuators. When we refocus this thing on orbit, occasionally, because I'll show you, I think next, that instrument carrier is made from composite struts, and those composite struts dry out a lot when it's first launched into the vacuum of space, but then over the years it still releases more water vapor from the structure of the composite, and so it will slightly shift, and we have to compensate for that. And so we want to make sure those actuators are reliable. Yeah, please.
Quick question. In space, is there any potential contamination of the mirrors, like gas or humidity or something like that?
Yeah, the potential contamination comes from the spacecraft itself, right? This is water vapor that's outgassing. We have thrusters firing hydrazine into whatever the byproducts of hydrazine are. And there are requirements that require, these things are all in thermal blankets, and so there's some source of gas from under, not a lot of gas, but some gas under the blanket, and we have to design those vents so it vents away from the optics. You've seen pictures when things launch inside the fairing. It's not always perfectly clean. That's why we have a deployable aperture cover. So obviously the inside the fairing is as clean as possible, but things still get by. So we have a contamination budget for both particles and molecular contamination, and we have good estimates at every stage of testing and assembly, and then on orbit, how much contamination we expect, and the instruments have to live with that. And it's like the other estimates, it's conservative based on many missions that we've launched historically. There are only certain materials allowed. You can't have a lot of different plastics. They're just not allowed, right? They outgas.
How big is the sensor on that camera?
I'll show you. That's coming up in a couple more slides. Yeah. So I'm still talking about the primary mirror, and I'll get to the camera. But just I wanted to give you some idea of all the testing. This is 2+ years of testing at different levels of assembly before it's sent down to the launch site. And then measure performance before and after each test to make sure nothing's changed from the test. That's the main thing. So here's that instrument carrier I was talking about. So here is this composite square truss tubes. I think these are don't quote me on this, but I think these are about 5 inches on the side of the truss. You see the people here for scale. But these are these large composite trusses, and they're epoxied into end fittings made from titanium or Invar metal. And then there's these metal plates. These are where this is where the wide field instrument plugs into these latches. There's 2 out here, and there's 1 deep inside, so it's kinematically constrained to the right amount and locked into position. Same for the coronagraph back here. There's a large opening toward this person where the coronagraph would plug in. So this was a capability that was deleted because of that external review. Originally, we wanted robotic servicing, take up a new instrument, remove the old instrument, and plug in the new instrument. And that's what these latches were originally designed to do. But as part of a cost-cutting, we can build almost anything, but you have to rein us in a little bit, otherwise we'll spend all the money. But no, I'll talk a little more when I get to the spacecraft portion. There are other capabilities that we've kept, so we can refuel it robotically. But back to the instrument carrier. This is when it's arrived. It's unbagged and checked out, and cleaned, recleaned. And then here it is again in the large clean room. It's now got some Mylar blankets for thermal purposes. And you can see this is the coronagraph instrument that's being installed. And so it's held to by this fixture here on the end of this long beam. This beam has a cross beam back here with counterweights. So this is all perfectly balanced, and this is suspended from a crane up in the ceiling out of view, but these cables here to the center of mass here, and that crane just slowly translates. There's a person, I think this guy here looks like he has, or this guy, I'm not sure, who has the controller for the crane to move it into position. Everyone's carefully checking to make sure it's perfectly centered and hits those latches in the right orientation, and then it's bolted on, and then all this mechanical ground support equipment is removed. And over here is the wide field instrument waiting its turn. It'll be integrated next back into this volume up here from this direction here. Okay. So this was earlier last year. I want to say probably summer of last year. I'm not sure. But okay, now I'm going to talk about the cameras, the instruments, the capability. The wide field instrument built by BAE Systems, which was Ball Aerospace, has this set of capabilities for imaging and this set of capabilities for spectroscopy through a GRISM and a PRISM assembly. Here are 8 bandpass filters from half a micron, 480 nanometers, all the way out to the reddest wavelength, 2.3 microns out here for that filter. And some idea of the sensitivity in this row. Then the coronagraph provided by JPL, technology demonstrator, will do both imaging and spectroscopy in these wavelengths here. And it can also do some polarimetry. One of their filter sets has a Wollaston prism, so in a couple of light bands, it'll do polarimetry.
It has a filter wheel?
Yeah, I'll show you the filter wheel for wide field. I didn't have a great image for the coronagraph. I didn't have time to throw one in there. I cut a lot of slides out. I could talk about this for hours. Here's that wide field. Here's the sensor camera, finally, you've been asking about. This is the 18 mercury cadmium Te. What is the chemical? Tellurium. Thank you, Joe. Yeah, so that's the technology for these detectors. They're 4K by 4K, so 16 megapixels each, 18 of them, so over 300 megapixels total. Yeah. And you see the gap between how they're tiled together. This is the gap I was talking about that will slightly move the telescope between images to fill those gaps. Okay. Yeah, these are for sale, I'm sure. That's a good question. I didn't get the cost breakdown I gave you before was for the total observatory. It's not easy to find cost information for individual at this level.
So it's 18.
Yeah, a 6x3, six across, 3 down. So this curved rectangular field of view, you'll see that fits in the well-corrected zone of an off-axis 3-mirror anastigmat optical system.
And it's what, CMOS sensors? Or?
I think I'd say yes. You had to cut out the field finder.
I think so. I'm not sure. That's a good question. I'm not sure if they're
I
CMOS,
don't know
but
what else it could be.
yeah.
Yeah, CCD would probably take too much power.
CCDs.
What was the question?
What kind of sensor are they? CMOS or CCD? I'm not sure. I know the coronagraph ones are low noise CCD. I'm not positive about this one. I'm just not. I worked on a much higher level of assembly than individual. I should have known. Amateur astronomers would definitely want to know. How much does it cost? What can it do? Yeah. I think there are spare detectors that are not being used, but I suspect they will be used for,
If they focus this thing on Earth, they could probably see people.
That was expressly prohibited by the congressional mandate. Yeah, has to point out, not down. Yeah. Okay, so let's see, where were we? Okay, so just overall, this is just the focal plane. So it's part of the larger subsystem with the relative calibration system I mentioned, the cooling system, that radiative cooling, the filter wheel I'll show you next. All that together is about 500 kilograms, consumes 370 watts, and the data volume, 11 terabits per day, generated by this guy.
Micro SD card?
I'll show you. I'll show you. So here's those aft optical module channels that get over inside the instrument. There's one fold mirror, and the pupil element in the filter wheel, I believe, is next. Yeah, there's the filter wheel. So these are about 100 millimeters in diameter, 8 bandpass color elements. I believe this is the prism and this is the grism. You see the grism has these a lot more mechanical stuff going on here in the mount, and then a dark field stop. But this grism, or excuse me, the prism. So I believe this is maybe this is the prism, this is the grism. Sorry, but it has a calcium fluoride optic, so very difficult material to handle, manufacture. If it's stressed, it'll induce birefringence. So you have to barely hold on to this thing, but it has to survive launch.
What's the benefit of those materials?
So it enables the spectroscopy that you want to do in those wavelengths. I don't know the details, but I think you could. There are probably scientific papers that explain it, but I just don't know. Yeah. Okay. I'm including things. I have a couple more things like that. I just want to just kind of like the unusual stressful details you have to. It's not just one single piece of glass. It's this fragile glass. Not this one, but I think another optic was just broken in the middle of fabrication, just from handling. It breaks, and then hopefully you've had spares in the pipeline to not impact the schedule. So there's the wide field plugged in. There's a nice shot of the radiators, and then it goes deep inside the instrument carrier with the relay optics to intercept the beam from the secondary mirror. Okay. Here's optical performance for spectroscopy and imaging. So, told you, the birds were attacking. I said something wrong. But this is a little hard to read, but from like 15 nanometers in the blue to 100 in the red. So you see these poorly corrected zones lie outside of the squares this is where the detectors sit, and so they're in this sweet spot of the 3-mirror anastigmat. And over here on the imaging side, it's from 27 up to 50 nanometers, so slightly better corrected, but still, you see the squares do intercept a little bit of red in some of the corners. It's unavoidable. Okay. Moving on to the coronagraph. So this is the first coronagraph in space with this active wavefront sensing and control, and demonstrating the technology of the hardware, the algorithms, the ground processing. I believe there's some ground in the loop, it's called, data processing to help correct the optics. So it has to communicate to the ground, do some processing, and then correction tables are sent up to the deformable mirrors to help correct the wavefront. Do you have a question?
Yes, please. The final aspect ratio, if you're going to move the telescope and fill in the gaps and stuff, what are you going to end up with for the final aspect ratio?
I mean, it's an all-sky survey. So some of those surveys I mentioned earlier on, they're concentrated at either high latitudes or in the galactic bulge.
So they just get stacked together and bigger.
Yeah, you want to. It's a survey that you want to take a census. Like, do you remember it was Kepler was the spacecraft that was imaging extrasolar planets like in one portion of the sky. It was just staring at one portion of the sky. And it found a bunch of exoplanets, but the question remains, is that true for the entire sky? And so then it was TESS, the Transiting Exoplanet Survey Satellite, that did the same sort of job, but across the entire hemisphere, both hemispheres. Okay, so that's what, we don't want to answer these big science questions and then have some question remaining. Well, maybe that only applies to this little patch of sky. So it depends on the specific type of science. You just want a sample number, a large sample number of whatever target that you can say reliably, this is true for the entire universe, say. So that's a very high level question to ask, but it is answered probably in that report, in that New Worlds, New Horizons report, because we have to say that we can do this within 5 years of the primary mission, right? We have to survey this many square degrees of sky, find this many extrasolar planets, otherwise the results are not statistically valid for a survey, right? Okay. So it's all about high contrast, that, seeing that, firefly next to the searchlight, the planet next to its star. So high contrast imaging, spectroscopy, extended source imaging, and polarimetry. So these are all the components. This is the optical layout. The blue light, I'm not even sure where light comes in from the telescope, but it ends up, it hits, the main cameras are this yellow-green one up here, and this yellow-green one here, and this is, I believe, these are beam dumps. So these are the main cameras up here, and then these DM1 and DM2, these are deformable mirrors I'll talk about more that correct the wavefront. So the blue light is the blue rays are this is the optical ray trace for this instrument. And this is one deck. This is the optical deck, and there's another deck on top of this of, right, time? Okay. There's another deck with electronics, thermal control. So this is like stacked together like 3 triangles and then put into the instrument carrier. Okay, so 300 kilograms, 340 watts of power, and quite a smaller data rate, only 0.8 terabits per day when it's operating. So this is I mentioned earlier, interferometrically, you split that beam into 2, and then you shift it 180 degrees with respect to each other, and then that cancels out the starlight, and hopefully you have the planet's light left over. So with their process for doing this is called digging a dark hole. Your target star has the planets, it's somewhere in this noise, but you want to first, before you image the target, you image a star nearby that you don't think has planets, and you make this field as dark as possible, correcting all those optical aberrations I talked about. And then once you have that prescription set with your deformable mirrors, you shift over to the target, image that guy, or that star, and then you subtract the two. And hopefully you have some bright spots left over that are planets. You can repeat this whole process by rolling the telescope around its bore site, let's say up to 30 degrees, and then hopefully these planets will roll the same amount around the center. And then you've confirmed it. Okay. Okay, so these are simulated images. So 47 Ursa Major, this is already known to contain planets from that spectroscopic red and blue shift from ground-based telescopes. So we know roughly where these planets are, and then simulated this mathematically with the expected performance of the telescope. This is what we think the coronagraph will be able to do. This red circle is kind of the inside limit. We can't see inside that zone. We'll see the zodiacal disk of dust, hopefully. And then this is another simulated image. I'm not sure what the colors mean in this image, but standing out is a warm Jupiter. This is a distance of, let's say, 3 parsecs, 10 light years, 14 parsecs, 45 or 50 light years, I believe.
Outside of our solar system.
Yeah, these are stars, extrasolar, not outside the galaxy. In our galaxy, but within, I forget. I think it depends on.
Within 1,000 light years or something.
I'm not sure what that outer range is. It probably depends a lot on the type of star, the type of planet, where they are together. But you basically you dim the star by a factor of 10 million or so, and then you can see the planet nearby. Okay. So here, these are those deformable mirrors. Someone asked how you correct that wavefront. So these are 48 by 48 actuators in that deformable mirror, just rows and columns. And it has this electroceramic actuator, so you apply a voltage or a current, and then the actuator moves a little bit and deforms the mirror in that location. So this is how these are just goofy and less goofy test images in the lab, showing you what you can do with 48 by 48 pixels. This is another one of the engineering challenges that they noticed. These were sensitive to humidity, again with the humidity, but the focus and astigmatism changed at different levels of humidity, and so they just purged it with dry nitrogen and calibrated it in place, and we keep those settings for on orbit. Okay. Here's boy, that's a low resolution picture, but this is that beam and that ground support hardware. This is the coronagraph and all the low resolution imaging of the connectors that's going into the instrument carrier over there. Then this is that main contrast requirement, 10 to the 7th flux ratio or signal to noise ratio, brightness of the target star, 10 hours. So that's the main requirement. And we have to try to verify this on the ground. This is contrast on a log scale from 10 to the minus 4 down to 10 to the minus 8, and iteration. So they have some control scheme. They change some settings, and then they re-image, and then they're zeroing in on the target. These dashed lines here around 10 to the minus 7 are the requirements for coherent and incoherent light. And eventually, after a couple, 3 days in the test chamber, they do better. And they thought they could even do better. It was getting better at the end, but you can't run the test for as long as you like. Other people are waiting for the chamber. You have to get your equipment out and assembled to the next level. But they meet this requirement with 80% of margin. So you always want to see that kind of number. Here's again a picture of that optical deck, technicians assembling something in the JPL clean room. You can see a little bit here. These are heaters on the composite. the composite deck. There's different scenarios where if the observatory has to go into safe hold mode, and we're not maintaining. This is for any observatory. You're not maintaining proper attitude. You first want to stay power positive, thermally balanced. Sometimes the instruments will need their power. We can't continue science in that kind of a contingency scenario, so we pull power from the instruments, and if they get too cold, they'll break. So the spacecraft will send survival heater power to the instrument. We control that. We're monitoring their temperatures of the instrument, and they have their own heaters and control loops when they're operating normally. But in a survival mode, the spacecraft controls this so it doesn't get too cold and break. That's what I suspect. These are either operational heaters or survival heaters. Okay, and that's all controlled by the spacecraft. So, little more than half of the mass, 5,400 kilograms, 2,200 watts. The solar arrays are capable of more. After 10 years on orbit, the solar arrays produce less power, so we size them for that margin. The overall architecture are this aluminum honeycomb panels that make up those triangular bays, and then light-weighted aluminum decks on top and bottom. This blew me away, the wiring harness, just the wiring. I don't have a great shot with the panels open, but there's these huge trunks of wires, something like 45 miles of wiring that weigh 400 kilograms. And all those wires have to be checked out. And
All that little space?
yeah, but it's not a little space. There are two people standing over here. They're behind a little ways, but this is a fairly large spacecraft.
A harness is a good word for it.
Yeah, it's a wiring harness. So you connect this component to that.
Better hold it.
Yeah.
That's the wire harness.
Yeah.
So there are some. There's a better picture in the next slide, but there's these red covers. This is where the thrusters are, so they're delicate. We want to cover them up during ground handling.
You said 2,200 watts?
Yeah, electrical power.
At what voltage?
It's around 28, 30, 32 volts.
So it's pretty much standard panels that they're wired in series.
We wire things
Series parallel.
both ways for redundancy and reliability. So if one set of electronics fails, we switch over to the second set. So it's and then you have to have, by adding extra components to be more reliable, there's ways of cross wiring things to
You don't lose the power.
so you're
Power remains.
yeah, that's exactly. So stable and reliable, and so there's different ways to get the same effect. Somebody asked me about the memory earlier. There's a 10 terabyte flash memory data recorder, and so we need about 4 terabytes of storage for the data. Data gets ingested and then sent down through the communications equipment to Earth, but you want some storage there in case the ground station needs to go down for a day for maintenance. We keep all that science data and we'll send it down to the ground eventually, so we don't miss any. This is right at the limit, 500 megabits per second from almost 1 million miles away. This is right at the limit for radio frequency transmission. If it was a little bit more that we needed to get back, we'd have to go to optical laser communication. And then very fast internal data link from that wide field instrument, from that focal plane array and the focal plane array electronics over to the spacecraft is a very short, very high speed data bus, 250 gigabytes per second.
Hey, John,
Please.
is the communication equipment, is that a power hog?
Say
power?
is which piece of equipment?
Communication equipment, radios, is that a power hog? Sure seems like a lot of data. It's got to be
It is.
processing all the time.
I have not seen it's I'm sure in the hundreds of watts. I would guess low hundreds of watts, but I'm guessing. So I could find out for you. But that's a combination. That's one of the ways to get a higher data rate, more power through the antenna. You can have a bigger antenna, and then
He's the electrical engineer.
Yeah, okay. Yeah, but that's
Mechanical engineer.
that's one of the trade studies you would do early on, is how much power do you have available for communications, and then size the antenna, or pick the frequency band that you want to work in.
They got it down to the lowest.
Yeah, and that's I believe it's compressed as well. This is compressed data, so that's the third way of getting more data down, is you compress it losslessly, but you can compress by a factor of, say, around 2 losslessly. And then again, full for Class A risk posture, full redundancy, graceful degradation. So of those 18 detectors, maybe we could lose 1 or 2 and then still continue on with the science data program. The reaction wheels I mentioned, there are 6 of them. We can operate with 5. We'll just be a little bit slower moving from direction to direction. And then where we do have a single point failure, like that aperture cover, there are, I think, the mechanical actuators for that door on top. I didn't really show a good picture of it, but there's only one mechanical actuator. So if it doesn't work, the aperture stays closed. So the way you get around that is to design for very high reliability. We have a lot of testing of engineering development units. We learned a lot from the James Webb Space Telescope. They had to do over 100 deployments in series, and every one of them had to work perfectly. And we were all very nervous, but it worked. And so we took lessons from them to design for reliability for these single point failures.
So,
Yeah,
there
please.
was a space telescope recently, I thought, that you had a problem with like lens caps that wouldn't come off. It was like an X-ray telescope. Have you heard about that?
Which one was it?
They still were able to operate it because the lens caps.
XMM. I think I know the one you're talking about. So this is XRISM, XRISM. I believe had an aperture door, and that's funny you mentioned that. So that instrument I worked on, XRS2, was a predecessor to this one. So XRS1, the original instrument, had a launch vehicle failure, went off course, the nozzle disintegrated, went off course and had to be destructed. The second one I worked on made it to orbit, but we had liquid helium stored cryogen that wasn't being vented properly. And when the aperture, I believe we have a guard vacuum around that liquid helium. And when we opened the valve to the vacuum of space, which is better than the guard vacuum, some of that liquid helium wasn't vented in the right direction, and it made its way around into our guard vacuum. So we lost all of our liquid helium after 30 or 40 days on orbit, and we can't do science with that instrument. Then the third, so we didn't get any science data. The third X-ray spectrometer in that series, at some point in the mission, went into a safe hold, and when it was, which is normal, they all do that. They're very cautious about how they operate, and then it goes into safe hold, and then coming out of safe hold, it spun up to like, hundreds of RPM, and then broke apart because of a sign error in some of the software. Instead of firing the thruster to slow down the rotation, they fired it to speed up the rotation by accident. Then XRISM is, I believe, the 4th X-ray spectrometer in the series. And what you mentioned there about the aperture cover not opening, they knew that there's a possibility that it won't open, right? Not every device is 100% reliable. So they built a window in the aperture cover. It's like a thin metal foil window. So X-rays can still get through to the detector. So the
thing was working even though not up to 100%.
Yeah.
But
So
even though the door didn't open, it was like
Right.
glass
right.
door.
So it's very complicated. It's hard to do.
Reasoning on
Yeah.
Yeah.
Okay, so moving on. A few other changes we made to the spacecraft. It used to be made from composite honeycomb, which is expensive but high performance, and then changed to aluminum. This servicing capability, I mentioned the instrument removal and replacement. That's gone. And the capability to work with an external occulting spacecraft, like a star shade between us and the target star. JPL was going to build a star shade, but we cut that capability we need some hardware on our spacecraft to do that. But we kept the robotic rendezvous and refueling. So a robotic refueler could grapple the spacecraft, and the fill and drain valves for the propellant are mounted externally where they can easily be worked on, and some other smaller changes. But here's another nice shot from above. You can see the little 4 sections where the propellant tanks are inside. And then here's some of that wiring harness. On the portion on top is just coiled up here, waiting to go up into the instrument carrier and optical telescope. This is set up for, you see some people on the side here. We're setting up for an electromagnetic compatibility test. We'll just blast it with different frequencies and make sure the conducted and radiated electrical noise does not mess things up. Here's, I think one of my last slides here is showing, here are the propellant tanks mounted to the bottom deck, to their structure. All the plumbing for the propellant is in there. And then it gets raised up from below into, here's the spacecraft bottom deck, and the spacecraft panels on the outside here, the thrusters on the corners. And this is built separately and then integrated with the larger spacecraft. And that's it. So I think, thank you. Thank you. So, any other questions?
Is the orbit similar to like a Hubble or something?
No, the Hubble's in low Earth orbit. This one's going out to Earth-Sun L2, where the James Webb is. There's a.
That's close to 1 billion.
Yeah, exactly. So on the opposite side of the Sun from the Earth, that's stable Lagrange point. And it's in a halo orbit around that Lagrange point, so that the Earth's shadow or the Moon's shadow are never, the spacecraft never goes through those 2 shadows. It stays outside of those cones for thermal stability. Okay. All right, thank you very much. Okay.